In this video, we take our first look at classes and objects in Java, and we start to see why we call Java an object-oriented programming language. This video is meant to be an add-on to the reading for this week. It's not meant to be a replacement for the reading. I will not be going over everything in the chapter with this video. The video is meant to be a brief overview and introduction of some examples that will help us think about the concepts in this chapter. So make sure you've done the reading before you watch this video. And the video is only covering about the first third of topics in this chapter through classes and a little bit about fields and methods. So first we're going to talk about classes. Classes are an aspect of object-oriented programming that allow us to define the objects that are going to make up our program. We've talked a lot about algorithms. I've told you that algorithms are a series of steps and that writing a program involves taking an algorithm that may be written in pseudocode or it just may be an idea of how to accomplish a task and translating it into computer code that can be compiled so that the computer can actually execute those steps. However, the execution of an algorithm is only part of what software does. Software also deals with data. And so the object-oriented approach to programming marries the data and the functionality, combining them in the form of classes that are blueprints for our objects that will interact. And as we go on, you'll see how that happens here. In software, particularly in object-oriented software, our objects each have two capabilities that are separate and work together. An object can store data and most often does store data, and an object can perform operations on that data. And we have names for these different capabilities of objects. Just so that you recognize the terminology, the data is often referred to as either attributes or fields. These are interchangeable terms. And we've already talked a little bit about how we refer to algorithms in an object. The operations or algorithms that are part of an object are called its methods. Strings are a great example of an object as an introduction because we've already started working with strings a little bit and you're familiar with the data that they store. For primitive data types like ints, they are much more simple than something like a string because they can only store data. So an int, for instance, only stores an integer. It doesn't have any kind of capabilities built into it to modify integers. But an object, like a string, stores its data but also provides some kind of functionality that allows you to manipulate that data. For instance, in strings, we can do things like get the length of a string, we can get the first character in a string. These are things that you have probably seen in the chapter material regarding strings and in some of our examples. So just to continue on with this example of strings, here's a representation of how an object works, and particularly a string. We create a variable with the name of the object that we want. So we're going to call this city name. We'll call this string city name. And when we create that variable, it stores an address that points to somewhere in memory where the actual string is stored. So this is different from a primitive because the primitive, when you create a primitive variable, the primitive variable actually stores the value of that variable. And this one is a little bit more indirect. When you create an object reference, like when you create the variable for a string object, you're actually only creating the storage for the address, and then that address will point to a place where the string data is actually stored. So this is a representation that just helps you think about that. So in this particular example, we had the string that was set to the value of Charleston. We can see how the string objects actually have a functionality that goes along with its data when we look at methods like the length method. The length method actually returns an int that contains the number of characters that the string object is made up of. For example, for Charleston, Charleston has 10 characters. So when you call the length method of this particular string object, you're going to get the number 10 returned. And in this case, this statement is assigning the value that results from this method call into a variable called string length that's an int. So left to right, how this works is this is declaring a variable, an int variable called string length, and it's assigning into it a value that is created when we call this string's length method. So city name is the string. We use this dot notation to specify that we are calling a method, and the method name is length. And these parentheses are for an argument list, but length has no arguments, so they're blank. We'll talk about what arguments are a little bit later on. So you can see that for any string, and this is something that all strings have in common, you can call their length method. Primitives don't do that. There's no int.length. It's just not something that you can do with primitive types, only with objects. So talking about objects, why did I bring up classes before? What is a class? And what's a class have to do with objects? Well, there's actually an intimate relationship between classes and objects. And we're using a metaphor here in the chapter in order to demonstrate that relationship. Classes are related to objects, like blueprints are related to houses, the houses that are built from them. That is to say, a class is a plan for a certain type of object. And once you design a class, once you create a class, you can make as many of those objects that you want. For instance, for the class string defines what kind of data and what kind of operations have to do with strings. And once that class string was created, we can actually make any number of string objects from that class. And those string objects all work the same way. Just like these houses all have similar structures. In fact, they're very much the same. However, these three houses, even though they were built from the same blueprint, are separate houses. They might have separate addresses, you know, they're in separate places. They're actually separate physical locations, but they are all they all have their plan in common. That's kind of the way, if you think about it, that's kind of the way strings are. Strings all work exactly the same way, but each string can hold its own data. For instance, in this example, you see we have 3 string variables, person, pet, and favorite color, and they all coexist in a program. So even though they're all strings, which act according to the same plan, they all actually have their own data. So they're the same in that they're all made from the string class, but they're different in that they are separate objects from each other with their own values. Whenever we make an object from a class, we call that instantiating an object from a class. To instantiate means to create an instance of. So another way to talk about an object is to say every object is an instance, a single instance of a class. For example, this string object is an instance of the string class. It's a single instance, a particular instance of the string class. This string object is also a particular instance of the string class. And this object is an instance of the string class because it's a string object. You can see the power here is in the fact that all these strings act the same way. In other words, you can do the same things with them, but they each store a different actual series of characters. And that's important because what you're seeing is that once you have a template for strings, once you have this string class created, you know that you're going to be able to create strings that will all behave the same way. For instance, you'll be able to get the length of all those strings, you'll be able to get the first character of all those strings, you'll be able to print all those strings to the console. You can do all the same things with them, and the data that they can store is very similar, but the actual particular contents of that string in each case of the string object will be different depending on the purposes that we have for it. So you can think about a class, like a string, as an abstract idea. Classes are defined to represent a single idea, a single concept or service. In the case of a string, that idea is the ability to store a bunch of characters that can be used as a name or some other purpose. All of our classes in Java have access modifiers, and there are other uses of access modifiers too. We'll get to that a little bit later, but I want you to be able to recognize these. You'll see them in the headers of classes and methods, and there are 3 access modifiers in Java: public, private, and protected, and they have separate purposes. The public access modifier tells the Java compiler that whatever resource that it's attached to is public, meaning that it can be accessed by any other class in Java. If you want to exert some more control over a resource, you can make it private or protected, and we'll talk more about what that means later on. But you'll see the access modifier showing up in the header of a class. The header of a class is something that you'll be familiar with from some of our other examples. For instance, we can take a quick look at, well, let me drag it down here. Maybe it's better if I squeeze this up. Okay. So here's what the class header looks like. You've got access modifier, class, and then class name, and then you've got the body of the class here with the class's members. What's that look like in one of our examples? Well, in class, we use the input snafus class. We had an example where we were reading information about dogs and cats. So here you've got public class input snafus. There's the access modifier, public. There's the keyword class indicating that we're creating a class, and the name of the class. And notice that it is represented here in the proper format, which has inner caps. This is known as Pascal case. It's got a leading capital letter and an inner capital letter there. And it's followed by a curly bracket and the class members. In this case, this class only has one member. It's a method called main. Member is a term used to refer to any resource in a class. So for instance, the attributes or fields of the class are considered members, but the methods are also considered members. Classes are designed to encapsulate both data and functionality, and this is really the primary idea of having classes and objects, is that the data and the functionality work together to accomplish some goal. And so when we design our classes, we want to think about the data and the functionality that go together. The data is really central to a class. It really defines what the class is. And in the example that I'm going to use a little bit later, you'll see how important the data is and why it really is the central part of a class. So that's the first thing that you think of when you think of a class. What data do we need to manage? Sometimes you can build a class around the data. But then you're going to want to think about what actions need to be performed on that data, like how the data can be modified. Does it need to be accessible? You think about rules about how that data should be modified, because most of the time you want to be able to control how that data changes and how it's used, at least to some extent. So in designing a class, we have a visual representation that allows us to summarize the kind of information that you'll find in the class header and information about the members of the class. We call this unified modeling language, and in particular there's a unified modeling language class diagram that lets us represent information about classes. You'll be seeing this show up in our work. You'll be seeing it in a number of places, so it's important to be able to recognize a UML class diagram. It will contain things like the class name, the attributes of the class, and the methods. I'll show you an example of this a little bit later on, but here's your first introduction to UML class diagrams, which is shorthand for representing what a class does. The attributes, as we mentioned, or also called fields, the data of a class, are the entire information that the class encapsulates. And a great example of this is a rectangle. If you think about a rectangle, what is it? Really, a rectangle, of course it's a shape, but the only information you need in order to have a rectangle is it needs length and width. And I'm going to build a whole example from this, this idea of a rectangle as an object. So you can think about, if you have an object that is a rectangle, that is length and width, what might you want to do with that length and width? How might you access that length and width? I'll let you think about that as we move on. And one aspect of objects that Java gives us some control over is who accesses our data and how it can be accessed. And we call this data hiding. I want to highlight one aspect of data hiding. The book stresses the idea that objects can use data hiding to become self-governing. In other words, if an object has much of its data or methods private, it can prevent meddling with its data from the outside world. But I'm going to also point out that by hiding data in an object, it makes an object really simple to use, because people on the outside using that object won't know about all of the inner workings of an object. This will become more useful an idea later, and I mention it now because it's going to come up in our example. So in addition to the data, in addition to the attributes or fields or whatever you want to call them in an object, we also have the functionality, which is in the methods. And methods have the algorithms that are used to modify the data. Methods have headers similar to the way that classes have headers. You'll have an access modifier, a return type, a method name, a list of parameters, and a method body. And back to our example here, here's a method, the main method of our input snafus class. It's got an access modifier. It's got a return type. We're going to skip over static for the moment, and we're going to look at this return type. Void is a return type. Void is no type, no return. We've got the name of the method, and we've got some parameters inside of the, let's show that, parameters inside of the parentheses just before we get the body of the method, which is where the algorithm for that method is implemented. Okay. So we think about the data that goes into an object, and then we also have to think about what methods we need and how they might work. When we're thinking about methods, we think about how the data needs to be changed or accessed, or what things can be calculated from the data that we already have. Maybe you can come up with a completely new thing that seems like an attribute of your class, but really it's just a secondary piece of information that can be calculated from the information you already have. Sometimes you have data in your object that you don't want people changing directly, so you give some methods of access and mutation of that data. In other words, you give people a limited way to get the information or set the information. We often call these setters and getters. This is what they look like. For a rectangle example, you might have a length field, you might have a width field, and in order to modify these, you could have a method called setLength. And when you call that method, you send in a new value for the length. You can also have getters. So instead of allowing people to access the length or width fields directly, you would have them call a method that returns the length or the width. Okay, at this point I think it's important to see an example of what this might look like. What it might look like to have objects in your program that are interacting defined by classes that you've written. So in order to show you what this looks like, I've created a program that has multiple classes in it. And as I said before, once you've got a class that's useful, like the string class, you can use it multiple times to make multiple objects. In this case, I've used the example from the chapter, rectangle, to actually create a similar class of my own called rectangle that we're going to use in a program called HouseCalc. And here are the UML class diagrams for this program. If you take a look at them, you might recognize what's going on here. According to the slide that we saw before, let's just look at the rectangle for a second. We've got a class name, rectangle, and then we've got the members of the class. First, we've got the fields or attributes, and for instance, it's got a length attribute and a width attribute. And I decided to make my rectangle an integer rectangle, so it's got an int length and an int width. And then following that, it's got a bunch of methods. It's actually got a method called rectangle, and we'll see what that means in a second. And then it's got a getLength, getWidth, setLength, a getLength, setLength, getWidth, setWidth, and getArea. And we'll look at those in more detail right now. So here's the class itself in code. Very much like the UML representation that we saw before. Here is the class header, which gives us the access modifier, and that is followed by the keyword class, telling us that this is a public class and the class's name is rectangle. And I've given the rectangle just two pieces of data, two integers, length and width. And now you're seeing, so for the first time in an example that I've used, I've given a class its own data. So why is this different from the data that we've seen before that has been inside of the main method? Well, this data belongs to the class. It's outside of any method, which means that these two ints are part of the class. They're not local to any method. You may also notice that rectangle does not have a main method at all. Okay. Main methods are you only require one main method per program. So when a program runs, it's the main method that is the first algorithm that starts stepping through when you run a program. So if there's a class in your program that is being used to create objects that are used by the program, but those classes themselves aren't their own individual programs, then they don't need main methods. You'll see how this works in a little bit through the use of this example. Okay, so this rectangle can be created when its constructor is called. We haven't talked about constructors yet, so I'm not going to go into this in detail, but here's the constructor for rectangle. What this constructor does is actually takes two numbers and creates the rectangle from them. But I want you to take a look here at the getters and the setters for the data in the rectangle. So if you want to get the length, you have to call this method, getLength. If you want to set the length, you have to call this method and send in an int, and that sets the length. Why do you have to do that? Because I made the length and the width attributes private, meaning that classes outside of this rectangle won't be able to access them. To access them, they have to use these public methods. These public methods are accessible, but the actual data itself is not directly accessible. So as a bonus, we've got length and width, but we don't have area as a field. So because area is not an attribute of this class, I created a method called getArea, which provides you with the area calculation, multiplying length and width. GetArea is a public method. It returns an int because its return type is int, and the method is called getArea. And when you get area, it will take the length, multiply it by the width, and return that to whoever called the routine. All right, so this is the rectangle class. This is not a rectangle object. This is a class. Objects will be created from this class, and those objects will be rectangle objects. Okay, here's the program that I wrote in order to use the rectangle class. It's called HouseCalc. Its purpose is to act as a utility for realtors who need square foot calculations. Okay, so in other words, it's going to create the 3 floors of a 3-level house, and it's going to sum up the square footage on each floor. So you can see how rectangles are useful for this purpose. I'm just going to step through what each line of this program is doing so that you can understand how this program makes use of an object of a class that I created. So here we've got the header for the entire class, public class HouseCalc, and like some of our other programs, HouseCalc only has one method. It only has one member, it's a method, and it's a main. So this is where the program is going to start running. So it's a public method, return type is void, main. The first thing that the HouseCalc program does is it declares 3 rectangle objects, first floor, second floor, and third floor. So look at that. We're actually creating variables, and the type of that variable, these variables, is not a built-in type anymore, like int is, not an object that was given to us, not a class that was given to us by the Java class library like string was. This is an actual object that I created for this project. You're going to do the same thing. You'll be creating objects that your own programs will use. So I make 3 variables of type rectangle, and then I declare an integer, an int, called total square footage, which is going to allow me to do some arithmetic and store the result. So then I immediately take my rectangle variables and I use them to make new rectangles. This is what it looks like when you call the constructor of an object. If we go back quickly to rectangle, you see that there was a method in rectangle where if you called it, you had to send in 2 ints, and then it would take those ints and it would use them to set up the internal data of this object that is private. So it will set the length and set the width. So even though you can't set them directly, there are plenty of ways to set them indirectly. For instance, using this constructor is one way. So for each of these variables, we create a new rectangle, which means we take the rectangle class and we instantiate a rectangle object. We give it its initial values, and then we store it, each of them, in one of these variables. Now, I'm just using the print line statements to kind of show you what we can do with these objects. And just looking at this first statement here, we're going to focus on the first floor. I am writing to the console, the first floor is, and then I want the length in feet by the width in feet. And so what I do is I concatenate in here the integer, the int that gets returned when you call this rectangle dot get length. So first floor dot get length will return the length. First floor dot get width will return the width. How do I know that? Well, I can go back to the rectangle and check. Get length returns length, and length is an int, so I know that this call returns an int, and it's going to be stuck into this sentence here. This program tells us the dimensions of the first floor, the dimensions of the second floor, and the dimensions of the third floor. Very much, each of these is very much like the others. Then, to put a value inside of total square footage, we do some arithmetic. We call first floor dot get area, and we add that to second floor dot get area, and we add that, all three of these together, third floor dot get area, and the result of this addition, calculation is assigned into total square footage. So again, going back to rectangle.java, we can see that get area, all that does is it multiplies the length times the width, and it returns that int to whoever calls it. So that's what's going to happen when I call get area. It's actually going to call rectangles get area method and return the area for that rectangle. And then of course here we print the total square footage to the console so that the user knows the answer. Now for each of these get areas, we're going to get a different return value because each of these floors was initialized with a different set of dimensions. In this case, the first floor is 60 feet by 40 feet. The second floor is 40 feet by 40 feet. And the third floor is 20 feet by 20 feet. It gets smaller as you go up. But it doesn't matter because each of these rectangles has the ability to calculate its own area. And that's what's going on here. So let's run it and see how that works. It's going to ask me to save that first. So here, this doesn't have any user input, so it runs very quickly. It's going to tell me the dimensions of the first floor, the dimensions of the second floor, the dimensions of the third floor, and the total square footage, which is this value. So one thing you might notice is the only data that you see locally defined in this main that's primitive is the total square footage. We don't have to keep track in this particular method. We don't have to keep track of each rectangle's size. That data is stored in the rectangle objects themselves. So you can kind of see how this works together. This single class keeps track of the length and width, gives you the area if you ask for it, gives you the length and the width if you ask for it. It's a neat little package that does this management of the rectangle all by itself. Now I want to show you that we could do the same thing without having any rectangle class. And it doesn't look that different, but it does look a little bit different. So here's HouseCalc 2. Notice I don't create any rectangles in this program. So I've got all my integers here, all ints. Instead of having the rectangle class that we can create objects from that manage this data, we're managing all this data here. Notice that we're saying first floor length, first floor width here, second floor length, second floor width. Okay, and then we're doing the calculation here for area instead of leaving it to the rectangle object. So it's not super ugly, but one of the nice things about the program that is using an object of type rectangle, it's a little bit more explicit what's going on here, because we've put the functionality that is out in the open here into a single class that we can create multiple objects from. So that functionality is sort of encapsulated or embodied in this class, rectangle. So we're also allowed to name it. So the meaning here is much more clear. We're creating 3 rectangles. Each of those rectangles represents a floor. And we're getting the attributes of those rectangles when we need them. And in fact, we have an attribute that is a secondary attribute that's calculated from primary attributes, but it really doesn't matter where it's coming from as long as we get the correct area when we call it each time. If you look at the other program, you can see that it's actually multiplying these two things, but the idea that it's an area is kind of lost in the code. So to some extent, good code is a little bit self-documenting, and so seeing these well-named attributes of the rectangle class helps with the readability of this code. Okay, I hope this example was helpful to you. Look in the description on YouTube for links to both HouseCalc, HouseCalc 2, and the rectangle class in case you want to try this out in your own copy of Eclipse. If you want to mess with it, change it, modify it, play with it, I am making this code available for you to do that.